So today I will dare to say that it will be the most important lecture of my lectures in total. Arguably the most important lecture. Yeah. My plan is to, if I do it well, if I don't get stuck, my plan is to derive the primordial power spectrum, finally, which is a quantity that you have heard now and then in my lectures and in Roman's lectures. It's been mentioned many times, so it is time to finally see how it comes to be in inflation, right? So in single field solar inflation. So let me remind you that the outcome of last lecture was to get to this point where we perturbed space-time. That means we discussed how to write the metric in a perturbed universe. And we decided that this was, it was a decision. We adopted the comoving gauge where the metric adopted this form. And remember that there was something pretty interesting going on with this choice. And this is that the inflaton fluctuation was set to be 0. Yeah? It is not deep at all. I want to stress that. This is just a choice of coordinates where we shut down the perturbation. And remember, part of the explanation, that the perturbation really arises somewhere else. And it is translated into, it is moved to B. Yeah? So remember that in this gauge, B coincides with the gauge invariant quantity, which is called the comoving curvature perturbation, which is R. Yeah? So this is only in this gauge. In other gauges, B is not related to R in that way. Yeah? So it's just convenient to adopt this gauge where you know that B is equal to this gauge invariant quantity, which is an observable. Yeah? So observables must be gauge invariant. Yeah? Okay, so we will get to the power spectrum of R. Yeah? For that, I want to, and because I'm also getting prepared for tomorrow's lecture, I want to propose that we do it with what is called the ADM formalism, which is a beautiful formalism to deal with gravity in general, which consists of writing the metric in this way. Yeah? So let me explain a little bit what's going on. Yeah? So, okay, you can see the G00 term, the G naught term. You can see the off-diagonal terms here. And here you have the spatial part of the metric, yeah, just Gij. I just call it Q, which is very conventional in this formalism. So Qij is just A squared delta Ij, okay? And if we compare to the other side, sorry, there's a mistake here. Perhaps you noticed this. This is 1 plus B, right? Or plus 2B maybe. I'm really sorry about this. It's probably 2B. Let me just check. Yeah, it's 2B. Let me just make that correction. Yeah, okay. Now we're back on track. Yeah. Okay, so this is 1 plus 2B. Again, there it is. So please compare what you have at the left-hand side and what you have at the right-hand side. They look a little bit different, right? So I want to make both sides equivalent. I think this part is ready. Yeah, you agree with me? The Qij, you look at Qij here, they're the same. Yeah. The part that is not so the same consists in G naught naught, which over there looks like that. Here it looks a bit different. Yeah. And this part also, which is the off-diagonal terms, which I call Ni there and Aj here. Yeah. But they're really not so different because remember that we're only dealing with scalars. We're not interested in vectors. And this is a vector. It looks like a vector, right? It has a spatial index I, so it's a 3 vector. But we can just given that we're dealing with scalars, we can just claim that this has to be the gradient of a scalar, yeah? And if I do that, then it looks exactly as it looks over there, yeah? So we just say, okay, this has to be A, DIC, and now they match. Well, not completely, right? You disagree with me. Why? Because here we have 2A, and there we have this combination. Well, it doesn't matter. I just redefine A, that's all. You agree with me? So now it matches. I just say, well, what I call here minus 2A is just all this combination plus 1, and that's it. Okay? And now we have the complete match. I'll allow you to do that. What really matters here, in moving from that description to the ADM description, which it has this notation, is that the content has to match. There we have how many scalars? 3 scalars. How many scalars do we have here? 3. So the number of degrees of freedoms is just the same. Okay? We already chose the comoving gauge, so we already killed 2 scalars. Remember that, last class, last lecture. And now I'm over with that description, and I prefer to work with the ADM description, that's all. But the number of degrees of freedoms continues to be the same gauge choice. So this is the ADM description of formalism in comoving gauge, if you want. Having said that, I will now relabel, in this case, Qij and Ni and Ni in a more convenient way, in a way which is actually more standard in the ADM description. So what I will do is well, first of all, I will erase B here, and I will say that this is just R. Okay, that's the first thing. I've done nothing, right? Because you know that B is equal to R in the comoving gauge, so I've done nothing. But now I will do something a bit more interesting. I will actually promote this to be the exponential of 2R. Okay? Why I'm doing that is, well, in a sense, I've done nothing, really, because this coincides with that when we linearize, right? So we're back to... But this is a very convenient way to deal with R, because it defines it provides a nonlinear definition of R, yeah, to all orders, yeah. We just need to agree that this is what we're going to call R, is the one that appears in the exponential. That's it, yeah. So perhaps your R is given by this combination, but my R is given by this combination. So this is yours. This is mine, yeah? So as long as we agree with that, we're fine, yeah? There's no way to get lost. I prefer mine, so I will stick to mine, yeah? Okay, that's it. And what about this one? Let me remember exactly how I will call it, because I don't remember exactly. I will relabel it also, but also the relabeling means absolutely nothing. Just trying to find it. Okay, here it is. I will, well, normally, let me rise the index, okay? It's just technical details. We rise it with Qij, by the way, in the IDM formalism. So Qij serves to rise and lower indices in this formalism. So I prefer to write it with normally we write it with a raised index. So this is going to be 1 over a squared, and then here, I'll just commit the crime of putting it down because it's just a derivative, right? So if you want, it's Qij, but Qij to the first order, so, well, too many explanations, doesn't really matter. And we will call it psi, okay? Just to match the literature. I want you to see the typical symbols that appear in the ADM formalism. That's all, okay? Okay, so I won't say too much about the ADM formalism, yeah? Except for the fact that if you go to Misner, Thorne, and Wheeler book, which is, you know, the book, right? It's a massive book with lots of beautiful pictures. And there you will find a beautiful illustration of how to interpret this parameterization geometrically. And I encourage you to go to that book. My plan was to draw it here I cannot compete with those beautiful drawings, so I will not do it. So please check out that book, which is it's pretty amazing. Yeah, but one thing to do at least to give some justice to this notation is that when you write the metric in its line element form, it actually becomes quite compact in this notation. So you see that it is written in this way, which is part of the geometrical interpretation, actually. And you will find that this takes this form. And so see how beautiful the metric becomes. Yeah. So, well, I'll do at least one picture of some sort of geometry. So you can see, if I draw, we have a manifold. We have a coordinate system describing physics in this manifold. So a given slice, spatial slice, we can parameterize it by time. So we say that this is some spatial slice at a given fixed time in this coordinate system. Remember that what we call time here is relative to a coordinate system that we choose. And so what I can tell you is that the metric Qij describes the 3 geometry of this slice. Yeah, okay. And so what you can do next is, for example, is grab your Qij and then compute, for example, the Riemann tensor out of Qij, which is the metric of 3 slices. So you only deal with you deal with just conventional geometry, differential geometry, but now only confined to the 3 slice. That's all. And then, sorry, my notes are dumping. Okay. Then you can compute, for example, the Ricci tensor, and then you can compute the Ricci. Yeah, that's it. Then there is another important quantity, which is called the extrinsic curvature, Kij. It's normally labeled, and its definition. Yeah, you just build it, and that's what ADM did. Please go to that paper. It's cited in my notes. And you will find that it adopts the following. It has the following definition. Yeah. So I don't have time to explain all the meaning of this, but Kij basically describes how this surface is curved in the whole 4-dimensional geometry. Yeah. So, and that's why it's called the extrinsic curvature. Yeah. So we have a Qij, which describes the intrinsic geometry, yeah, inside the surface, if you want. But that surface, because it lives in the 4-dimensional space-time, the rest of the geometry is described by Kij. Yeah? And now notice the following. Well, no, not yet. Let me now write for you the action for the Einstein-Hilbert term. Please. Okay, let me answer by writing the Einstein-Hilbert action. Okay, so remember that we are describing the evolution of the universe, and for that we write actions, Lagrangians, and our action describing inflation has 2 parts: the Einstein-Hilbert term and the term that describes the evolution of the scalar field. So let me first write for you the Einstein-Hilbert term. So this is, remember that we switched to Planck mass, so it has this form. And then the ADM formalism puts some emphasis on foliations, right? So spatial foliations here, time foliations. So we're foliating time, space-time in time and space. So that's why now I will not write d4x, but I will write d3x dt, because we have chosen some framing where we make the distinction between time and space. And now, what used to be the square root of minus d, in this parameterization of the metric, it simplifies quite a lot. It becomes n multiplied by square root of q, of the determinant of q. Yeah? It's a feature of this way of folating space-time using this parameterization, first of all. I will come back to your question. And then you have, look at this. The 3 Ricci appears alone. Yeah? Before it was the 4-dimensional Ricci, but now it's the 3-dimensional Ricci. And then we have the extrinsic curvature in this way. So notice that here we have the extrinsic curvature contracted with itself in this way, and here we have the trace of the extrinsic curvature squared. Okay, so be mindful that k is equal to, well, just that, the trace of the. Let me just wrap up the answer. Well, essentially, this is why I'm adopting the ADM formalism, because you can see sort of the geometry of the 3 folation and then the extrinsic curvature, they sort of split. Yeah. Does that answer your question, or your question was really in a different direction? Okay. Yes, no, and I'm not explaining that because that requires you to get your hands dirty and do all this computation and see that this really works. Yeah. Here, these are just definitions. Yeah. The real challenge is to grab your 4-dimensional Ricci and shows that it's equal to R3 plus Kij minus k squared. But that's not all. It's a bit more messy. Here you have gradients, divergences of something. But given that in the action we were integrating, they vanish. Well, you can make them to vanish in the boundaries, and you're left with only that. Yeah. And for that, go to MTW. Yeah. It's a good source for saying it. It's not too complicated. It's just I cannot do it here because it will spoil the objective of this lecture. Thank you very much. I never put names to these objects. N is precisely called the lapse function, and Ni is called the shift function, right? And your question is, can you repeat it? Okay. So did I answer you by just telling the names? Yes. So this is just a scalar. This in principle is a vector, but we just, given that we're only analyzing scalars, this will be this gradient over there. Yeah. Any more questions? Okay. Why am I adopting this formalism? There is some lesson here. Remember that we're now doing a parameterization which, for these definitions, right, for this R and this psi, all the content is there. All the 3 scalars are there. Yeah. But this formalism tells us which scalar is dynamical and which are not. Just look at the action. Where are the different scalars? First of all, N was what? Was A, right? Was representing A. But now it's encoded in the form of N. N is here, first of all, as an overall factor. Where else is N? It's over there. Yeah? And it is nowhere else. That's it. Yeah? And there is no derivative. There is no time derivatives acting on N. They're unknown. What does it mean for N? It's not dynamical. Yeah? is basically a Lagrange multiplier. So it means that when you vary the action and you see all the equations for all the degrees of freedoms, n will respect a constraint equation. That means that at best, it is solved by a Poisson-like equation, if you want. Right? So you just need to know the boundary conditions, and you know n. That's it. End of the story. There's nothing to evolve for n. N will depend on what other degrees of freedoms are doing. But the same can be said about ni, the shift. If you look at the role of the shift, there is no time derivatives. In fact, time derivatives are only in one place. R describes the geometry of spatial folation, so there are only space gradients here. Yeah? So there are no time derivatives. The only place where there are time derivatives is there to be seen, is just a plain view, is here, nowhere else. So this is the only dynamical quantity in DR, actually. This is a general statement. This is why ADM constructed these formulas. It is to see what is really carrying the degrees of freedoms. Yeah? If you only have a DR and nothing else, no other matter fields, then that's where the gravitational wave lives. Yeah? You agree with me? That's where the tensor mode lives. Yeah? But here we have adopted a gauge where we moved the scalar fluctuation to R. Right? So now R it is dynamical, yeah, and therefore there is a time derivative of R here, yeah. So you can see that in this formalism we see that to every order in perturbation theory, this is not just a linear statement. To every order in perturbation theory, R is the dynamical quantity here, and the lapse and the shift are constrained, follow constraint equations. They're not dynamical. They're just Lagrange multipliers. Okay. That is the lesson to be learned. By the way, if you want to write the action for the rest of the action, which is the scalar field one, let me do it for you. So we have this. In this formalism, it adopts this form, squared minus 1/2 Qij. di phi, j phi, minus v of phi. That's it. Now you see the whole action, but the important lesson is the one that I just said, is the fact that you can see by eye that the only dynamical quantities are. Don't need to do much more than that. Just count the number of degrees of freedoms which have a time derivative, nothing else. Okay, I think I can erase here. So the next steps are a lot of work, yeah, but is basically is straightforward. There is no tricks whatsoever. It's just spending a good weekend, maybe this one, yeah. And enjoy yourself with a good computation, yeah? And there is a lot of fun. And I will tell you a few elements. For example, I just deleted here Qij, but you remember, Qij is basically the exponential of R, yeah? So grab Qij, plug it in the standard definition of the Ricci scalar. Well, you go first through the Riemann tensor, Ricci scalar. Just perform the computation, yeah? And take a long time to do it. Just don't make mistakes, yeah? And then you will reach this expression. And it is valid to all orders in perturbation theory. This is why we like it so much, because if we're interested in computing nonlinearities, then this is a useful result. There you have. And now you can see, by the way, why this is called the curvature perturbation is because the Laplacian acting on it gives you back the curvature, okay? It really gives you the curvature of spatial slices, yeah? Okay, What else? You can also learn, I'm not sure I want to write this one, but okay, I already started. Unfortunately, I'm just wasting time, but, and all of this is in the notes. I'll do it as quick as I can. Okay, this is one part, and then -1/2 of that's it, and then the last part. Okay, don't even bother writing that down, it's in the notes. It's just the result for Kij with the parameterization that we're following with R, yeah? And it's given by this. Remember that Nk, the shift, is given by this gradient of psi, yeah? Oh, my fellow lecturers are so much better at writing small and ordered than I suffer going from one place to another. Okay, and now in this side of the blackboard, I will do my best to tell you what happened. It's not very good. I'll do it in yellow. This is better. Okay, what happened when you take these two quantities and you plug it here, okay? And this includes the scalar part, okay? So the scalar part you have to perturb also, yeah? But remember that the inflaton perturbation is not there, it's dead. That makes life so much easier because this will be 0 altogether, yeah? Because the inflaton, remember, yes, is the background part plus the perturbation. But we adopted a gauge where the perturbation is 0. It's not there. And so this part of the story actually becomes quite manageable. But still, you will face some terms here that are not dead, and they talk with the other part. Yeah? It's a nice challenge this weekend. Huh? Okay, so the action becomes the following. And I really want to write this action because it will be useful for tomorrow when we discuss the computation of the bispectrum. I hope we get there. Okay, so okay, sorry for, it's all in the notes, by the way. I hope not to, no, I just made a mistake already. I was doing well until, let me see. Yeah, sorry. I will open up. This has a lot of parentheses. Now I think I'm on the right track. Okay. Okay. And you know what? I think it's silly to write all of this because it's in the notes and you can see it. But it has a lot of more terms. Please excuse me for doing this. And even more terms, so it was going to be a long writing, but if you go to the notes, let me tell you at least which equation I'm discussing right now. And because I don't think you will take anything out of this. I just wanted to have it as a result, but it won't be really useful for anything else, just to stare at it. So this is equation, give me a second, 688. Yeah, okay. It's just a long equation, but it has some value. It is valid to all orders in perturbation theory. That's why we cherish this expression. Yeah? So please look at it at the notes. It's not really enlightening to see the form, but after a while you learn to read it, but not for today, okay? But for the weekend, please have a look to it. And then only now, I will say, let's do perturbation theory. Yeah? So I would say, well, n, the lapse, let's write it as 1, which is its unperturbed value. It's its background value, yeah, plus a perturbation. Okay? Here is where A lives, by the way. Okay? Just look at the original metric that I erased already, and you will see that 1 is just the background value that we've been discussing so far, and delta n will be the role of the A perturbation, the first perturbation to G naught naught. Yeah? Okay, cool. So we define that. Then that's it, because R is already perturbation. So we just say, okay, whatever you have, for example, this, well, you have to expand it. Yeah. So you expand it to 1 plus 2R plus 4R divided by 2 squared plus so on and so forth. So you do that expansion. Yeah. And so forth. I mean, you do this everywhere, and also you do it for Ni. Yeah. So remember that Ni with an upper index was parameterized in this way. Okay. And so delta n is small, R is small, and psi is small. And now you expand this. It's a long work, I promise you. Yeah? So, and then I'll spare you all the work. I've done it myself. And I will only do it up to quadratic order. Okay, so I want the linear description of the system. Tomorrow, we will look into the cubic part of this. But remember, you take these expressions, you put them here, and you don't worry about cubic terms. You only keep quadratic terms, and you have to check that the linear terms will cancel out all of them, and you are only left with the quadratic part. Yeah, and the result will be the following. Things will start looking a bit better now. I think it's fine so far, and then I'm not left with any more space. It's psi, by the way. Okay, and gosh, this is my fault. Okay, there it is. Sorry for that, okay? It's a quadratic action now. But you see all the elements. You have R, you have psi, and you have, what else? What was the other? Delta n. Can you spot them? So here is R, obviously. Psi is there. Here is delta n, so on and so forth. I think delta n is in various places. Any questions so far? It's all just computations. Yeah. Right. Cool. I'm going to do it now. Yeah? Yeah. So I can erase here. These are all really lengthy computations, but they're all done by somebody else. If you want to go out this weekend, don't worry, you're not forced to do it. Now we will vary the action not yet with respect to R. We will do it first with respect to the Lagrange multipliers. Yeah? And it so happens with Lagrange multipliers, when you vary the action with Lagrange multipliers, given that they don't involve time derivatives, you solve them, and you're allowed to plug them back into the action. Yeah? And so if you vary the action with respect to psi, well, just vary the action with respect to psi, that one over there, the quadratic action, you will find an equation. It's very direct. You will find that delta n minus r dot over h has to be 0. That's the first constraint that you find. Okay? Which means that delta n is married to r in this way. Whatever r does, whatever the time derivative of r does, delta n has to react to it. Yeah? So the first metric perturbation, A, finds out about what's R doing, what is B doing in this way. Yeah, they're in this gauge they're tied in that way through the constraints. And then if you vary the action against delta n, you will find the following result. Psi, I mean, I will not show you the equation, you just solve it and you end up discovering that psi is going to be epsilon a square over nabla square acting on r dot minus r over h. Okay? Maybe some people is worried about this. Yeah? What the statement here is that this is a solution of a Poisson equation. Yeah? So this is the solution after imposing boundary conditions. There's nothing more than that. Whenever you see the 1 over the Laplacian, it has a meaning. Yeah? 1 over the Laplacian doesn't exist. It's the outcome of solving the some Laplace equation, yeah? Some Poisson equation. Okay, any questions? Next step is to take those two solutions for the constraint equations and plug them back into the quadratic action, which is over there. Remember that this is the quadratic action. And there is still some work to do, but I will not do it. It's just to play a lot with the terms, do partial integrations. At the beginning, it looks messy. You grab those things, you put them there. You see that becomes even longer now, the action. But now you start moving things around. There are a lot of cancellations. And finally, here comes one of the main results of today. The action acquires this form. Which is a real beauty. It really collapsed down to something which is extremely simple. Extremely simple. Yeah? And so this is the action describing the evolution of curvature perturbations during inflation. Okay? Well, it could be any other epoch. It could be just any scalar theory, because remember that epsilon is defined in a given way. Epsilon is just the derivative of h. Yeah? Minus h dot divided by h squared. So this is quite general. This is just the description of how, it describes how curvature perturbations evolve in a universe filled with a single scalar field fluid. That's it. And this is the answer to quadratic order. That's it. There is nothing else. Yeah? Yeah, you grab these results. You grab this one. This is, by the way, the problems suggested in the notes. You plug them here. Yeah? There, etc., etc. And you get that. That's it. Nothing else. Okay? Don't try to think, don't do it mentally, because it's a long computation. You won't really get too far right now. Yeah? Good. This is an important result. And it's so simple. And it's also, let me emphasize, this is a gauge invariant quantity. So it's, everything is there. Yeah? If you didn't choose a gauge to work with, you will have arrived to the same result, by the way. Okay? It's much better to choose a gauge before doing it. This is a gauge invariant result, so you will have arrived to this, you like it or not. Yeah? But whenever you can choose a gauge, do it. It's an advice, because otherwise, to make the whole expression collapse into this is really difficult. It's just a lot of guesswork, and it's better to do it in an informed way. Okay. What I want to do now is the most important part of today's lectures, is to quantize R. We're going for that. But you already know how to quantize scalar fields. We discussed that, even in time-dependent backgrounds. We covered that, enough of that. Yeah? Remember that epsilon is defined as h dot over h squared, and eta is defined as epsilon dot over h epsilon, so on and so forth. And something you can learn, for example, from this equation, it's quite direct, is that you just integrate it. I leave it to you. And you will learn that this is for later usage, but we need something out of this, is that this becomes some value of epsilon times eta plus, log of A depends on t, so this time dependence of epsilon is through the scale factor. Yeah? And then you will discover that this doesn't stop here. This argument of the exponential continues, but the other terms are quadratic in slow roll parameters. So if I want the main contribution to how epsilon changes, it is contained by eta. I don't need to go further. There are more terms, remember, but those are subleading, yeah, because you start finding powers here of slow roll parameters and powers of log of A, yeah, log of A squared, for example, so on and so forth. Epsilon naught is defined as the value of epsilon when A is equal to 1. We are just choosing some conventions for A. This doesn't mean much. Yeah? And then you can discover something similar for h of t, that this is going to be essentially some value of h, which I will call h naught, multiplied by minus epsilon of log of A. Looks very similar to the one above, because essentially it respects the same equation with respect to epsilon, plus corrections. And the corrections also satisfy the same. They are just subleading. Yeah? They're just quadratic terms with respect to the slow roll parameters. So we can basically just say that in the end, the part that we are interested in looks like this. Take a look. That's true. If we neglect higher order corrections, but we're saying that slow roll parameters are small. Yeah? So far that was not true, but now we are imposing that. We're imposing that slow roll parameters are small. Please. Yes. Yeah, okay. Well, you can. Probably you're right, but a phi dot square can be traded by an h dot because of the background equation. So yeah, I think that should be going on there. Yeah. Okay. Thank you. And here I can also write this as epsilon naught times e to the eta. Okay. And given that we're stopping here, we can also call it here eta naught, epsilon naught, because we're stopping at quadratic orders. So we're ignoring subleading terms. Yeah. And then with this statement, it is very useful to work with this action to introduce what is called conformal time. I think you're not new to conformal time, right? Yeah? So conformal time is just a way to write the metric in a more elegant way, which is, so I will talk about tau. Tau will be conformal time. So now the scale factor will be a function of conformal time plus minus d tau square plus dx square. So we will do that parameterization. Yeah? So I stop working with t, I start working with conformal time. So notice that conformal time, okay, I'm looking at the background metric, right? Because I'm already taking care of the perturbation. So now I'm defining conformal time over the background. Yeah? So conformal time is just defined as dt over a. And then this is explained in the notes. You can integrate this relation. You can use these expressions over there. I'll leave it to you. I just want to get to the result as quick as possible. And then you can get that tau, let me call it minus tau, can be equated to 1 over a h 1 minus epsilon. This is a very useful result. This is true in backgrounds where epsilon and eta are small. This background, by the way, I haven't said that, have a name. These are called quasi-de Sitter backgrounds, okay? Because epsilon and eta are small, that means that h is almost constant. If h were constant, it will be de Sitter, okay? And that's a maximally symmetric space-time, blah, blah, blah. But here, we are not looking into that limit. We're looking into the limit of where epsilon is not vanishing. So therefore, we are dealing with a quasi-de Sitter, almost de Sitter, because epsilon is very small, but not quite. Yeah?
So in that equation, you can see, for example, that in the exponential, it appears
are you correcting me? Sorry. Are you referring to?
No, that's correct. But what I mean.
Wait a second. Let me fix this because this is totally wrong. You were all realizing that this was very wrong, except for me. Okay, now it's correct. Please, sorry, please.
So A in inflation changes a lot, right?
Yes.
So then you have, in the exponential, you have A. Of course, it's with a logarithm.
That makes a difference.
That makes a difference.
Exactly.
But
That makes the whole difference.
it
Yeah.
changes slowly.
Exactly. So in the end, you better look at this part, where as long as epsilon is very small, A can change a lot, and it won't matter too much. You will still be close to the original value.
Maybe you will talk about this when you talk about the R-cube term. You see, the kinetic term is not canonically normalized.
Not yet.
Yes, epsilon is small.
Yes.
That means that when you canonically normalize, the interaction goes up.
Absolutely. But we will get to that tomorrow. Yeah. Yeah. It's a good observation, and that gave a lot of headaches 20 years ago, yeah, to some people. By the way, here tau goes from -infinity to 0 in the way that I solved this equation. Yeah, it's the range of values. Conformal time in a quasi-de Sitter space-time is a bit funny. It only has negative values. That's why I wrote minus here. Yeah, and it goes from -infinity to 0. So 0 means the infinite future in cosmic time. Okay, so that there is a challenge for you to set your mind to that funny aspect of this conformal time. Yeah. So you can see that in the far future, A is as large as you want, and so you get to 0. Yeah. Of course, there is h, and h can do stuff, but we are in quasi-de Sitter, so epsilon is very small, so h doesn't change too much. And then for later usage, I will tell you that also that you can invert this relation, thanks to those over there. I'll leave it to you. And you can find an expression which is valid for for A as a function of tau. And this will be the following. Okay, that's it. Please keep this somewhere for later. Okay, we move on now to this was a warm-up to quantize the field. I want to quantize this field, but I needed first to tell you something about the background itself, that is quasi de Sitter, that things around are not changing too much, yeah? Except for A, of course, yeah? Now that I have clarified the background and I have introduced conformal time, what I want to do is to quantize that field over there. Remember our attitude, first lecture, that Lagrangians just contain the ingredients that you decided to put, right? And so this is the Lagrangian we have, and now we're going to talk about the quantum version of these fluctuations, yeah? And so we're talking about quantum fluctuations that live in the epoch of inflation. Yeah? And we have to make some decisions. We have to decide, where do they come from? You have to help me to make that decision in a moment. Yeah? So first step, let's make a redefinition, Sturani's definition. Yeah? So I will redefine R, and I will define a new field, U, okay? And this will be defined as the Planck mass. Well, the Planck mass is huge, by the way, Ricardo, if you're comparing these two things, so that's a caveat of your comment. Maybe you can set it to 1, and then we're back to being not so huge. A, R, that's the redefinition I want. So in other words, I'm saying that R that appears in the action is just 1 over Planck mass to epsilon A times U. So grab this, put it in the action. It's much simpler than the previous manipulations, actually. So, and you will obtain, you play around with partial integration, as you did also in the future, in this weekend, as you did with this huge action to get to that simple action over there. And here's what you will get. You will get 1/2. Am I missing a? No, I think I'm a. No, it's fine, it's fine, it's fine. So this 1/2 comes from this factor 2 over there. That is put on purpose. Okay, d3x, d tau, and here you see. U prime squared. Prime is a derivative with respect to tau, by the way, with respect to conformal time, please. Yeah? Okay. Minus nabla U squared, and then plus A squared, H squared. I open up. 2 minus epsilon plus 3/2 eta plus stuff which are quadratic in the slow-row parameters. So I will just ignore them. They're subleading. Yeah? If you're interested in a more complete computation, you can do it, no problem. Yeah? But I want to stick to the leading contributions. Yeah? And now we have U squared, and that's it. We got this to this point. So notice that we have something very similar to the original one, to the original action for R, but now we have a new term appearing, yeah, with a factor 2. This comes from doing partial integrations, because when you plug this over here, you have a time derivative acting on this A, okay, and that produces an H, yeah, and given that this appears squared, it produces a 2H squared, okay, it's just part of the computation, okay. And then, next step, if you're writing down this expression, do it fast, because I want to change it a little bit. Then use this yeah? Use this. Also use the expression for h, yeah? Grab them, it's really not too complicated. You plug them here, okay? And this, in fact, I'll tell you here. Oh no, we have it there. This is direct. Look, so AH, it was not complicated really. A squared, this comes directly from there. A squared, h squared is equal to 1 over tau squared, 1 minus epsilon squared, which expanded to first order in slow roll is just 1 over tau squared, 1 plus 2 epsilon. That's it. I'm keeping up only the leading term. The 2 comes from the squared, and the plus comes from going from the denominator to the numerator. Yeah? So after doing all of that, I told you to write this fast. This last term becomes the following. Becomes minus 1 over tau squared. I open up here 2 plus 3 epsilon. I'll do this in red. We'll write it like this. Minus 3 epsilon minus 3 half eta. Close this. Close this. I'm sorry. Here, there is u squared, and then I close the full parenthesis. Okay? It doesn't look nice, but it is what it is. And this is the result. Okay, let me stop for a moment. What we just did is to perform a field redefinition to simplify the action for R, and this is what we got. Yeah? This term, if you know anything about de Sitter spacetimes and playing with scalar fields in de Sitter, you will actually recognize that action. It will look familiar to you. Yeah? The action without the yellow part, without this part, is just the action for a massless scalar field in de Sitter. And it so happens if you study how a massive scalar field behaves, this is the action for a massive scalar field as long as this term is identified with the mass divided by h squared. Okay? So we have that this is the action for a massive field in de Sitter where the mass satisfies minus 3 epsilon minus 3 half eta. Okay? The equation of motion derived from this action is the following. Exactly. If you were dealing with a massive field, sorry, in de Sitter, this is nothing like that. This is R. This is the Curvature relation. But if you start with pure de Sitter, no gravity, just a curved spacetime, just curved spacetime without gravity, and you write the action for a massive field, that's what you get. Okay, fair enough. I think so. I hope so. I'm not sure right now. I think yeah. What else could it be, right? With m being the second derivative of the potential. Yes.
Can it be
Well, don't be worried if this looks negative. It can be negative, by the way. Yes, the answer is yes. But don't worry because this is not really a massive field. It's just a way to interpret what's going on. Yeah. That's all. So don't take it literally. The equation of motion for this has the following form. I'll keep working with the mass for now. Huh? Has this form. Remember that m squared over h squared is that over there. Yeah? But that's the equation of motion for a massive field in de Sitter. And now, what is there to be, what is there left to be done? If you pay attention to my first 2 lectures, I think you should know what to do now. To not embarrass myself, I will not ask you what is the next step. We have to quantize. This is an equation valid for the field operator. Yeah. Now that we know that the Hamilton equations are consistent with the action that we were working with, so on and so forth, so we can promote, well, not promote, just work with the algebra of commutators. And then we need to solve this equation by placing some ansatz. So our quantum field, U, is just a Fourier expansion of what? Of mode functions, which depend on tau. Creation and annihilation operators, there you have, plus EIK dot X, so on and so forth, plus the hermitical, the conjugate. Okay, now we need to solve, we need to plug this equation, sorry, this answer back into the equation, and this will lead to an equation which looks like the following. I don't know why, I don't need that. So that's the equation of motion we need to solve. Do you remember when we were dealing with time-dependent backgrounds that we had a time-dependent mass? Well, if you compare the 2 equations, this is the time-dependent mass. Yeah, it goes as 1 over t squared. Yeah, strange, but that's the way it is in quasi-de Sitter when you work with conformal time. So now we have a very precise equation to solve. Do we know the solution of that equation? Yes, there is an analytical solution. Let me show you what's the expression. With?
The solution is analytic for constant m.
Exactly, yes, yes. But slower parameters are small, they vary small, so that we can take it as constants, yeah. Or you can just work with the next order terms and make it more complicated. You can do perturbation theory about the slower parameters. So you can go quite far with this solution if you want. But it's quite unnecessary. Okay, here it is, the solution. Integration constant, alpha k, just to make it similar to our discussion on Monday and Tuesday, minus pi tau half, e to the I pi nu. I will tell you what is nu very soon. And then a Hankel function of the first type. Okay, that's it. Then we need the second integration constant. So I will write it like that, just to match it, to make it similar to our first lectures. Then we have the conjugate of what is above. And then we have the Hankel function of the second type. Given that the arguments are real, in fact, this is just the conjugate of that one. Yeah? But they can be defined for complex values too, so it's better to define first and second type, kind Hankel functions. Okay. I haven't told you what is nu. Nu is just the square root of 9/4 minus m squared over h squared, which you can expand in terms of slower parameters. I will do it soon, not yet. Remember that m squared over h squared are proportional to slower parameters. It's a small mass, if you want, but negative. Yeah, okay. Obviously, unless you are super familiar with Hankel functions, I guess with drums, no? They emerge when you study the harmonics of drums, or not? Am I mistaken? Does anybody remember? Yes? So unless you have worried too much about that, probably none of you really know how these guys look, right? I will not tell you yet how they look, but I will at least tell you some properties. Well, okay, no, go to Wikipedia. It's the best source of information about these functions, yeah? And then compute the following, just using the properties of Hankel functions. Do you remember how we call this combination? We call it, in the context of the second lecture, right? We saw this combination. We call this the Wronskian, remember? And remember that in time-dependent backgrounds like this, there is a condition on the Wronskian, yeah? It must be equal to I. That's the condition. If this is equal to I, then the field is quantized. It satisfies the quantum commutator between the field and the canonical momentum. The canonical momentum, by the way, I didn't mention this, but I hope it's obvious. The canonical momentum is U prime. Yeah? Okay. So grab this expression, plug it here, go to Wikipedia, and obtain the following result. This is equal to I times alpha k squared minus beta k squared. You get that. You can see that I chose a lot of factors here, pi, 2, whatever. Yeah, all of this is chosen very carefully in order to arrive to this, just to make it very similar to what you already knew from Minkowski. Yeah? I prepared it in advance. I mean, this is not what you will find if you do it the first time. So now we see that the condition requires that this is equal to 1. Yeah? We impose that condition, and we're done with the quantization. Yeah? Not quite, right? Because we still need to choose the values of alpha and beta. How do we choose them? Unfortunately, we're not in Minkowski. Remember that in Minkowski it was easy to choose alpha and beta. We just declared that beta is 0 because blah, 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 blah. Remember that discussion, yeah? What we will do here is to grab our solution and contemplate it and look at its form, yeah? If you draw it, yeah, you will realize that there is an interesting limit, which is k tau much larger than 1. That means let's explore what happens when the argument is very large. Yeah? Remember that tau is negative, by the way, so it means this argument to be just very large. What do you think it means when we take k times tau to be large? Any idea? Well, let me enlighten you a little bit. If you explore that limit, this limit here is the same as k over a tau being much larger than h. Does that help you at all? What is this? Let's first identify what is this. This is, well, first of all, k is just co-moving momenta, right? Thanks to de Broglie, yeah? It's 1 over the wavelength, yeah? 1 over lambda, or 2 pi over lambda, right? But okay, don't worry about the 2 pi. K is just the co-moving momenta, but k over a is the physical momenta, yeah? Just if you examine how a particle of a given momenta, use de Broglie to think about this, a particle moves in an expanding cosmology, the momentum of the particle decreases, right? because of the stretching of the wavelength. Yeah? So this is just physical momenta, if you want, which depends on time, because the quanta being described loses, is just being diluted. And bigger than h means we're examining wavelengths much smaller than the Hubble radius. Wavelengths much smaller than the Hubble radius is the same as momenta much larger than h. Yeah? So this is called the sub-horizon limit. Yeah? We're looking at mode functions where the wavelength is much smaller than the Hubble radius. What do you think? Imagine that you're of the size of a size much smaller than the Hubble radius. It's not difficult to imagine, right? You're all much smaller than the Hubble radius. So how does your environment look like? It feels as in Minkowski, right? You're in Minkowski. Yeah? Okay, so let's examine this limit. What will happen with the... It so happened that in that limit, you get the following result. Sorry. And what a surprise. We got exactly the result we got for Minkowski. It cannot be a surprise, right? The mode function, which is a scalar field, for very short wavelengths, that means a lot of energy, yeah? You're unaware of that the universe is curved, yeah? Your wavelength is way smaller than the Hubble radius. You don't know the universe, the universe looks flat. And you get back to something which is pure Minkowski. We saw this already, yeah? So it should not be a surprise, right? It's the way it looks. And now we need to take a decision about alpha and beta, but we done that already when we worked with Minkowski. We decided at that time that we will take bk equal to 0, beta k equals to 0. That decision is already taken. So here we're taking a stand. We're saying that fluctuations, when the wavelength is way smaller than the Hubble radius, they look like vacuum fluctuations in Minkowski. Remember that this decision had to do with how do we define the vacuum? So we're saying that the vacuum state is empty. The vacuum state defined as the one killed by A, by the annihilation operator. So by taking beta k to 0, we're deciding what are we calling the vacuum, yeah? And it's a well-informed decision. It's because we're saying at very short wavelength, the universe must look Minkowski, and we want the state of the system to be devoid of particles at the very beginning, at the beginning of inflation. Whatever, asymptotically into the past. Remember that tau being large means going back in time, yeah, for a fixed scale. So, having said that, let me go back here and let me just erase this term because beta is 0. Let me set alpha to 1. It could be a phase, actually, but it's an inconsequential phase. It doesn't matter what, so we just turn the phase to 0, yeah? Because remember, it's really this equal to 1, but that phase doesn't show up anywhere in any computation, so it's up to you. And so this is our final solution for the mode function. Still, I haven't told you how does H nu looks like. I will do it in a moment. But at least you know something about, I mean, I just examined, this is Wikipedia, by the way. Just go to Wikipedia and ask yourself how does H nu looks when this argument is very large. It's an asymptotic expansion of Hankel functions, that's all. It's not, nothing really strange went there. Okay, so now, remember that this is not the star of the story. The star of the story is R, the curvature derivation. And it is given in terms of U as 1 over Planck mass, square root of 2 epsilon, A, UK, yeah? So I prefer to show you how does R looks like in a plot, not U, okay? And then remember that I prepared you in advance that you know how does A look as a function of tau. So just plug it there. You also know how epsilon looks as a function of tau, by the way. Yeah? So do that. Just replace it. And then you should obtain the following. You should obtain, you just fill in what's going on. And then you will have, you have that. Strictly speaking, I should put knots here just to signal that those are the values of the slower parameters when A is equal to 1, which is just a choice, divided by the Planck mass square root of 2 epsilon naught again. So there is, you see tau present. And now we need to multiply this by UK, okay? Now, there are two sources of time dependence here. One is in UK, which depends on tau through these combinations. So tau appears here, here, and that's it. But also tau appears here through this factor. That's super important, as a matter of fact. And what I will do now, yeah, I'm never moving too much around. I will erase here also. Please, please. Yes. You're worried because this is blowing up for tau going to 0. Fair enough. Yeah. Right. Yeah. So you're thinking about the limits here, about tau going to 0 and tau to infinity. My advice is not to get too distracted by that fact. This here, this is very deceiving. You might be worried about that, but this is an effect of the curator of space-time. It's just that this is a Minkowski, this is de Sitter term, if you want, yeah? So indeed, if one spend too much time looking at this without really working out the equations of motion, you might think that this combination really, at some point, blows up compared to that. But in fact, if you grab those, if you want to compare really, you have to grab the solution there, and then compare how large is this compared to this, and you will find that they are of the same size. Yeah? So basically the solution, remember that here you have U. Yeah? So this U behaves in such a way that this will not be such a damaging thing. Yeah? So don't just look at this. Be aware that this guy is also depends on tau. Okay? So in the end, things do not really blow up. Are you satisfied with that answer? You have to explore it yourself, and you will marvel yourself by this fact. Yeah. So it's a bit deceiving, and I do recognize that this might be deceiving, but in the end, nothing really weird is going on. Okay. I'm almost done, by the way. How much time? I didn't think I was going to make it, and I'm almost there. Yeah, remember that nu, by the way, I don't want to forget that it was the square root of 9/4 times minus m squared. You expand the m squared of that relation, and then you get that nu is equal to 3/2 because of the square root of 9/4, yeah? And then corrections which are given by plus epsilon, and then plus eta half. That's what you get, yeah? So this is the value of nu here, here, that's it. Well, if you want, it also appears here in a sense, right? So in fact, now you can check that. That there is another limit. We examine the subhorizon limit when the wavelength is very small compared to the Hubble radius. Let's look the other limit. Let's ask, how does the mode function look when the wavelength is huge compared to the Hubble radius? That limit corresponds to k tau much smaller than 1. Yeah? Same logic as before. You just ask yourself, what is this? This is the physical momenta in units of h. And so we're asking when the physical moment is super small. Yeah? That means that the wavelength has been stretched way larger than the Hubble radius at the time. Remember, the Hubble radius is almost constant. And this expansion is going very quick, yeah? Regarding wavelength. And you will find that this combination over there, it goes as I gamma nu over pi times 2 minus k tau, which is positive, to the power of nu. That's how it behaves. Yeah, the Hankel function. This I took this from Wikipedia too. Yeah, and now this means that in that limit, now there's some magic here. Pay attention. Notice that this depends on tau. It also has k. They come together. But this doesn't depend on k. This is pure background. Remember, this comes from 1 over epsilon, square root of epsilon, 1 over a. Yeah? This is pure background. But see the way that the tau appears. Is it obvious or not? You will have to focus on this part. Yeah? There will be a cancellation. The time dependence coming from here, from the background, will cancel with that time dependence over there. That doesn't happen for k. It only happens for tau. K continues to be there, okay? So let me write you what happens with r k of tau in the long wavelength limit. I already told you it becomes time independent, yeah? And it precisely becomes this. It is only a function of k, yeah? So on super horizon wavelengths, for super horizon scales, r becomes insensitive of time. It just freezes, as I told you was going to happen yesterday. It becomes a constant, okay? Okay, I gave you 2 asymptotic limits. What happens for very short wavelengths? We decided to, what's the value of beta in that case? But now there is no more decision to take. This is just the prediction of inflation for the value of r when the wavelength is huge compared to the Hubble radius. Yeah? So this is the prediction out of inflation. Okay, this it is. Yeah? Let me now draw you what's going on. Let me make you a plot of, by the way, we can now put here nu, we can replace it by its value, which is 3/2. I neglected a few things, by the way. Just I'm sticking with the leading order terms. So this is minus epsilon, and then minus half, eta half. That has that form. Okay. And then if you plot this, so let's plot here rk of tau. And I will plot it as a function of a over h times k, which is nothing but 1 over p, if you want, in units of h. P being physical momenta. Yeah? It's just a way to visualize things. So the universe is, this is becoming large, the universe is expanding, right? So we're looking at time here for a fixed k. We're choosing 1k to explore, to see how it behaves. And you will discover that this will not come out so good, but I started awfully already. So it looks like that. Okay, so there are a lot of oscillations, which are huge, but then you start seeing something, it starts spreading, and then becomes a constant. That's the way it behaves. So into the past, it oscillates a lot. You know that because you know it approaches to Minkowski, the U field. Remember, we expanded the U field, but now we're seeing R. Yeah. So R oscillates a lot with huge amplitudes into the past when the wavelengths are subhorizon, but then as time progresses, this mode, the wavelength of this mode, is becoming of the side of the horizon. And this happens at this point when K over A is equal to H, when the wavelength is equal to the Hubble radius. This is called horizon crossing. So the mode function fluctuates a lot for subhorizon wavelengths. The wavelength is stretching, and then it becomes of the size of the horizon, and then the mode freezes. This is called the freezing of the mode function. To finish, I'm almost done. Any questions? Sorry. Any questions? Please. Exactly. This is proportional to epsilon and eta. No, because the way we are handling this is that what you see are the values of epsilon and eta for time when the scale factor is equal to 1, which was a choice. The deviations from that are quadratic in epsilon and eta. So here you're seeing only what is left, yeah? Which are the values of epsilon and eta in a very precise time. Of course, the values of epsilon and eta continue to change. But what you see there are specific values of epsilon and eta at a given time, when A is equal to 1, which we just fix, is any time you like, yeah? You just decide that you will call A equal to 1 to a given your favorite time during inflation. Yes, exactly. So I'm abusing of I'm making a use of language here. A massive field in de Sitter has nothing to do with a curative perturbation in quasi de Sitter, but it's useful to. Okay, so last step, I'll go here. And I'm almost done. Compute now the following thing. The square root of R, yeah, of the mode function. You know what is that? That's the power spectrum, remember, isn't it? Yeah. But we do it not for all values of K. We will only do it for superhorizon wavelengths, yeah? We don't care about what happens for subhorizon. We want the prediction of inflation for superhorizon wavelengths. Those are the initial conditions that Roman needs, right? So I don't need to predict for him what happens at superhorizon scales. That's the Minkowski regime, yeah? We will never be there, yeah? But the universe is full of these superhorizon wavelengths, so we need to compute this in the superhorizon limit. So I'll just square this, which is the prediction, yeah? In doing so, we get that this is equal to h squared over 4m Planck squared epsilon naught k cube over k h naught minus 2 epsilon minus eta. That's what you get. And of course, you know that Roman really doesn't want this prediction. He wants the scale invariant, sorry, the dimensionless power spectrum. So the dimensionless power spectrum, you just need to multiply this by k cube and divide by 2 pi square. Remember that? And we get this. So I'll do that. And this is equal to h naught squared divided by h pi squared epsilon naught and Planck squared of k over h naught minus 2 epsilon minus eta. There you have. This was the goal of today's lecture. It was to predict this value. This is the almost scale invariant power spectrum predicted by inflation. Almost, because you can see that it still depends on k, but very, very lightly, because epsilon and eta are small. Yeah? This here is called ns minus 1. That's the parameterization that it is often used when to measure this quantity. And this here is often called the amplitude. Yeah, let's call it A over S. And something I didn't tell you yesterday, I forgot, yeah, is that, remember this equation that related epsilon with epsilon v, and eta with epsilon v and eta v, yeah? I never told you that when epsilon v and eta v are small, epsilon just becomes equal to epsilon v. I think I didn't tell you that. And eta becomes equal to, I have it here, minus 6 epsilon v plus 2 eta v. You have to remember what are epsilon v and eta v. They are functions of the potential. Yeah? So you can see that by measuring ns minus 1, which is being measured, I mean, I would say with exquisite precision, then you're placing a constraint on the shape of the potential. Yeah? So you learn something about the epoch of inflation. You learn what's the shape of the potential when these mode functions exited the horizon at a very specific time. Yeah? So just one last word. If the, okay, he's not paying attention, so I will, use the opportunity, yeah, exactly. So let me provide the big picture now. It's in very few, just 1 minute. We plot this sort of the history of inflation in terms of the potential, right? So you can write the potential in this way, right? And this is just typical, yeah, with some minute value at the end, if you want. And so the infladon, which is here, really, but you can visualize it as a marble going down. The slope of the potential. Well, it's moving very slowly because of the friction term. Remember that, yeah? And that makes the values of epsilon, of h, epsilon, eta to vary very slowly, yeah? But as this happens, time progresses, the fluctuations are being, if you want, originated from the vacuum, yeah? So this is the two-point function computed with the vacuum, yeah, with the vacuum state. Perhaps I didn't emphasize this enough, but the state that we're choosing, we did that when we choose beta to be 0, yeah? We chose the vacuum. And so the infladon is progressing, and fluctuations are being created from very minute scale where the universe is completely empty, yeah? At a very short wavelength. You look at the universe, there is nothing there. But as the universe expands, fluctuations start to emerge, yeah? This is, who asked me the other day if this was called gravitational production of particles? Yeah, you are, I think, yeah, yeah. So you can imagine that that's going on, that the universe is expanding, the universe is curved, and you have this particle production being generated by the curvature of inflation, if you want. That's one way to see it. And the universe starts to get populated by these fluctuations, yeah? If you look at the state later on, it's not the vacuum anymore, not for those scales. It's now populated by particles. You can actually count them. There's a procedure to count the number of particles produced by inflation. And so these fluctuations start from the vacuum here, yeah? They fluctuate, they evolve, and then they freeze when they cross the horizon. And the marvel of this, the beauty of this, is that what you see here in these expressions are some background quantities. Apart from k, you have h naught, and you have epsilon, and here also. And so their values get frozen together with the fluctuation. The fluctuation exits the horizon at a given moment of the universe, and it registered how was the universe at that time. Yeah? Its amplitude holds that information. Its amplitude gives us information about this quantity, h squared over epsilon, and this can be measured. Of course, this has been measured, so we know the value of h squared over epsilon. That's great, yeah? But we also know the value of the shape of the potential through this mean, yeah? So this is not enough. We don't learn too much because these are just two numbers, and we have three parameters here. We have h naught, epsilon, and eta. Yeah? So we wish to have another constraint. This is not enough. Two constraints are not enough for three parameters. So tomorrow, I will predict in a similar fashion. This will be faster because we've done the hard work. I will predict what is the power spectrum for tensor modes, for primordial gravitational waves. And it's what will happen. We will find that the power spectrum for tensor mode goes as h squared alone, without this epsilon. So if we were to measure tensor modes, primordial gravitational waves, then we can have a hold on this, and now we're done. We know three very important parameters. H naught, the size of the Hubble radius at inflation, at least when the perturbation crossed the horizon, and epsilon and the shape of the potential. Yeah, that's the beauty of all this story. Well, thank you very much.
One or two questions before lunch.
What about chair?
Thank you, Gonzalo. It was very clear. But I have a doubt. How do you compute the not quantities?
The what?
H0, the not quantities. H0, epsilon 0, eta 0.
Yes, perfect. What I like about this expression is that it makes reference only to the way the background is evolving. Yeah. But you know that the background evolves via, for example, the Friedmann equation. Yeah. So the background evolves according to the shape of the potential. Yeah. So for example, remember that 3h squared is basically equal to v. Yeah. So by knowing the value of h naught, let's say, you know the value of v when the scalar field has a value which you can call v naught. Yeah. Up to you.
Can it be whatever you want? This
it could be whenever you want, because okay, we don't know which portion of this potential we're really observing. Yeah. Okay. Are we observing this bit when the perturbations crossed the horizon when the inflaton was here? Yeah. Or are we observing this bit? Or are we observing this bit? We don't really know. Yeah. So we must be somewhere before the end of inflation, of course. But this is the end of inflation. We have to look back. Our normal way to do it, this is an exercise, by the way, is to count what is called the number of e-folds, yeah? Which is equal to the logarithm of A divided by the A of the end of inflation, yeah? When the inflation finishes. Yeah? Please see the exercises. So we can go back in terms of how many e-folds we need. And normally, typically, I mean, people argue about this. It's not really an important argument. It's how many e-folds do we need since the fluctuations exited a portion of inflation, during a time of inflation. And those are the fluctuations that generated, for example, the CMB angular power spectrum. Yeah? So the CMB angular power spectrum is a constraint on a given region, of a given time. We see not only one scale, we see many scales. That's why we can measure this. Yeah? So the CMB covers a few numbers of e-folds, yeah, of inflation. But where exactly was this? We don't know, and people often suggest that this has to be 60 e-folds before the end of inflation. Yeah? But we don't really know that precise number. It depends on reheating, depends on a lot of things that are a bit messy. Yeah? But at least we can know the shape of the potential somewhere. Yeah? And that's already a lot.
Okay, thank you very much.
So, be quick.
I just wanted to confirm. So there are three free parameters: h0, epsilon 0, and eta 0. Is that so?
H naught, yes, H0, epsilon 0, and eta 0, precisely.
Okay, so
those are the three parameters that appear here.
I just wanted to get an intuition because, like, from the Friedmann equation, the value of the potential is defined by the H0, right?
If you want, yes,
Okay.
it's proportional to, yeah.
Then this sets the shape of the potential, and then the epsilon and the eta would set like the phi 0 and phi 0 dot, the initial conditions of the inflaton field.
Phi 0 dot. No. In the end, this becomes insensitive. Well, you can also think of what was the value of phi 0 dot, for example.
Yeah.
You will never be able to tell the value of phi 0 because the value of phi 0 itself depends on what is your model, what is your potential. Yeah?
Ah, okay.
But the whole thing that I've done is completely independent of the specific model. Yeah? So now you have to draw your favorite potential. Yeah? But this will continue to be useful. Yeah? You just translate. So this will tell you the height of the potential and then features like the first derivative of the potential and the second derivative of the potential here.
Okay.
That's what you gain.
Three parameters, one's the value of the potential, one first derivative, and the other second derivative. That's the idea.
That's it.
Okay.
Yeah,
Okay, I
precisely.
Thank you.
Yeah, thanks to you.
Okay. Calling once. Ah, okay. Last one. Last. Then we close.
It's very quick. Is this spectrum red tilted or blue tilted?
It is, this will be red tilted.
Okay.
It goes, yeah, I should, sorry. I'm sorry, Ricardo. This is answering a very important question. If you were to draw the potential, sorry, not the potential, the power spectrum, yeah? Let me draw not what is predicted, is what is observed. So what is observed is the amplitude of k over, you choose some value of the, where in which scale you want to observe, CMB scales, for example, then ns minus 1, yeah? And so you're asking about what's the value of this. It so happened that this is negative. So in a logarithmic plot, yeah? So this will be log of k. And so it has a slight slope, yeah? And that's it, it's going down. But you can understand it in terms of that this makes sense because this is basically telling you for a let's say k equal to h naught, let's forget about this term. The amplitude of this is proportional to h, but h is decreasing, yeah? So this is in a sense is registering the story of h. So there was a value of h here, there was another value of h here, another value of h here, so on and so forth. There is an exercise, again, in the lecture notes, where I ask you to derive the spectral index, not in the way we just did it. We did it in this very complicated way, but you can also derive it by just knowing what is the amplitude. It's a fun fact. Yeah? Look at that exercise. You don't need to know this. Just by knowing this, you can infer what has to be the right value of this. And the reason that is that h is decreasing in time. Yeah? And so there is only one way to get that. Yeah? So I recommend that. Well, but the epsilon can also be changing, so you have to be careful about that. Yeah? But it's a good exercise.
Calling once, calling twice. So we reconvene at 2.
Okay, thank you.
Maybe 2 minutes before 2 for taking the picture.
Ah, yes.